Let me introduce you here to the negative binomial and the hypergeometric distribution. Let's start. The negative binomial is a twisted version of the binomial distribution. Remember that the binomial distribution assigns the number of successes in a fixed trials. Negative binomial will twist the word success with the word trials. Let's say that we want to know how many trials will it take us to get 5 successes. Then the negative binomial is the sum of 5 random variables that each of them give us how many trials do we need to get 1 success. That is to say that the negative binomial is the sum of 5 geometric distributions. Take your time to think about it. Let's see the probability function for 5 success. This is equal to the formula we see here. P power 5 gives us the probability for 5 consecutive successes, and y minus p power k minus 5 is the probability of k minus 5 consecutive fails. And these here are the different ways to fit 4 successes in k minus 1 trial. Why we fit 4 in k minus 1? Well, because the last trial will be always a success. TYT. Now let's see the mean. This is easy because the negative binomial for 5 successes is the sum of 5 identical geometric distributions. Then the mean is 5 times the mean of the geometric distribution. Similar for our successes. Now for the variance, we use the same argument and the independence of the trials. Let's go now to the second subject, the very weirdly named hypergeometric distribution. This is the distribution that described the exercise in our MTG video here. But we will explain it in this video using a bowl of candy. This is the case. We pick small n candy from a bowl that contains big N candy. There is a total of C chocolate in the bowl. The hypergeometric distribution counts the number of chocolate that we can pick. Let's zoom out to continue. We give equal probability to each choice of candy. The probability function is the different ways to pick K chocolate from C times the different ways to pick N minus K non-chocolate from big N minus C over the different ways of picking small n candy from big N candy. Now we show you formulas for the mean and the variance, but we will not prove them here. You can think about the mean formula, but the variance I think is not worth it for the moment. Let's go to the boa constrictor. Okay, let's explain what we have here. First, we import some libraries into Python. These are the ones that we are going to use. Maybe it is too much. I am not an expert in Python. I am learning both statistics and Python, so I think I am allowed to have some mistakes here. If I do, please tell me. Here I have a list of elements. So this is a list that starts from 0. It has the number 0, 1, 2, 3, 4. And this will be the values that we will have for a random variable. For both random variables, we will use it for the negative binomial, and we will use it also for the hypergeometric distribution. For the negative binomial, we know that the values are infinite. We can have 0 trials, 1 trials. Well, we cannot have 0 trials. We can have as many trials as the success we want until infinity, because that can go until infinity. But I'm going to use until 7 because I cannot plot something until infinity, not that I know of. And we are calling the variables for the negative binomial S will be 2. This is the amount of success we want, and the probability of success that we have in each trial will be 0.5. What we have here is a list of all the values of the binomial distribution, negative binomial distribution from 0 to 7. But again, this could take from 0 to infinity. In Python, the negative binomial is not the amount of trials, but the amount of errors. So this k, if we want to compare this k with the k we have in the explanation of the video, we have to sum 2. We have to sum the number of success. But we are not going to use this list of values for the binomial. What we will use is a fake data, so data clones produced from a negative binomial, 80 of them. And this is a list of all the data that we create from the negative binomial, all the possible values that we can have. Well, not all the possible values, many values that we can have, 80 values that we can have for the negative binomial. So data clones. What it says here is the graph of this thing here. We have here a list of many numbers, and then this plot shows an organized way the numbers. How many times we have the number 0, how many times the number 1, 2, 3, 4, 5, until the number 7. Well, until the number 6. And what we have here is the plot of the negative binomials, of the probabilities of the negative binomials. And I am multiplying it by 80 because I wanted to compare with this data here, which has size 80. Now we do here something similar for the hypergeometric distribution. T will be the total amount of candy we have, C is the amount of chocolate in the bowl, and N is the amount of elements that we can pick from the bowl. This is another way to have all the values of the hypergeometric probability function. But what we will do is to generate 80 data clones and then compare it with the plot of the hypergeometric probability function. In Python, the name we use is probability mass function, not just probability function. Now let's run this program. As you can see on this side, there is the graph of the negative binomial. First, there is the fake data is in blue, and then the graph of the probability function in red. You can see that the fake data is not exactly the same as our probability function. It is generated by the probability function, but it can vary from it, as we can see from here. Now for the hypergeometric, we can see that it looks more similar, both graphics. And again, in blue is the fake data generated by Python, and in red is the probability function. That's all I wanted to say today. See you later, twisted person.